started. Okay. I think last week we were talking about chapter 3. And today we are actually going to skip chapter 4 and directly talk about chapter 5. Okay. As I had mentioned in the first lecture, it is we just don't have enough lectures in a semester to cover the whole book. So I'm going to select some chapters that I consider important, okay, or I probably would say more useful to you guys. I mean, to cover, okay. So chapter 5. What is chapter 5? Chapter 5. In the past, okay, when we talk about line segments, we talk about plane subdivision, right? But obviously, one of the most basic elements for a geometric object is point, right? Is point. Okay. So this chapter we are going to talk about point, but just like the previous chapters, okay, we are going to use problem to motivate this the following question that we are going to discuss. But the question itself, at least from the looking, okay, it does not look like computational geometry type of question, because it's we are talking about querying a database. Okay, so I suppose all of you here are at least a junior student, right? A junior. Okay. If you, in computer science, there are some basic courses that are considered, they are required. Okay, but there are also some courses that may not be listed as required, but I would highly recommend you guys to take. For example, okay, database. Okay, because you guys may know database has been so useful in current computer science area. Okay, almost just like networking. Okay, you can probably say that. Okay, before network become so popular. Okay, because now it's an AI, right? And previously it was cloud computing. Okay, and even earlier it was wireless networks and network in general, perhaps. But even before networking, it is database. Okay, I wouldn't. Of course, I wouldn't tell you. Okay, I wouldn't say database is a good research topic at this moment, because, well, it has been popular for such a long period of time. So a lot of I probably say easy questions have been taken care of. So it's difficult area to get into. But just because just like a network, okay, nowadays it has been database has been used in many different areas as a building block. Okay, so you probably want to, before you graduate, you want to take a database course if you have not done so. Okay, so to to abstract the database, okay, the ideal database, okay. Basically, like database contains like a large number of data, obviously, okay, and this data are represented by what we call attributes or features, okay, and of course, not all the attributes or features are numerical, right? I mean, like, for example, like, say, like, we have a table, database table for students, okay? Each student has a name, right? And you have a personal identification number, right? And you may have like your rank in the university, okay, and so on. So you can see that, okay, rank obviously is a numerical field, right? And as for like you know, ID, I mean, because like there's a like English letter initial, okay, followed by some number, right? So normally we treat it as like as a string, okay, and not to mention the name, okay, name is also we use string, okay, to deal with it. But think about this, okay, because you can encode the non-numerical field into numbers, right? I mean, we use the ASCII code to encode each letter into certain number anyway, right? So supposedly, like you know, as long as you know how to quickly deal with numbers, okay, I probably should say again. You know how to quickly search, how quickly like I mean quickly index the numerical field so that you can do the search very efficiently. That'll be great, right? That's the basics idea of database. So that's it. Okay. Here's an example. Okay. Here's an example. Okay. This is more like what should I say? Like employee database. As you can imagine, each employee has a birthday, right? Has a birthday, and we can sort of like convert each birthday into numerical field, because supposedly we have the birthday is stored in like in the year, month, and the date, right? But we could certainly you know convert those three fields into one single large number, right? So this may mean like 1950, and then the next two digits means the month, the last two digits means the date, something like that. Okay, so we can convert each birthday into a big number, and then each employee will have a well, salary, right? I mean, for this amount, I think this is more look like a monthly salary. Okay, the payment, the salary for each month for the employee. Okay, so and a lot of time, okay, we want to do what we call range query. Okay, for example, like okay, we want to find like all the employees who were born in from 1950 to 1955. Okay, so that is why, okay, the range is from 1950, 0000 to 1955, 9999, because this is the range that we want to search. Okay, and we also want to know, like, for this amount, for employee with this age, okay, what are their salary? Okay, we are particularly, okay, interested in those employees with this age, who are, whose monthly salaries between 3,000 to 4,000. So you can see that you can sort of like consider each employee as a point on this two-dimensional plane, and this query sort of will be converted into finding the point in a rectangle region, right? So how can we efficiently do that? Okay, so of course we could generalize this problem. I mean, when I say generalize this problem, what I meant is like, obviously, I mean, for database, I mean, a lot of time you are going to query, do a range query with like more fields, right? When you do a range query with more fields, say if you are doing range query with 3 fields, then your problem will become high dimensional, okay, like 3-dimensional situation. X-axis may be, the birthday, okay. The y-axis becomes monthly salary, and z-axis may be like the number of years that you work for this company, the duration you have been working for this company. And the range query will, and the all employee will be represented as a point in this 3-dimensional space, right? And your range query will become finding the point inside a certain, well, like it's like shape, okay, inside this shape, the points inside this shape, okay. So how do we efficiently do that? Even though, as I said, when we talk about the regular database, okay, we don't usually consider each field as a numerical number, but if we do that, we could convert this type of database query problem as a geometric problem. And obviously, we are going to deal with points, right? As I said, this is one of the most fundamental elements in geometric objects. Okay? So before we look into higher dimension, okay, I gave you example for 2-dimension, for 3-dimension, but let's try to simplify our discussion to an extreme. Okay, to extreme, meaning we consider 1-dimensional situation. Okay, well, for one-dimensional situation, I mean, you will have just a number, right? You have a bunch of numbers, right? And the range query becomes like a finding, like the entries in a certain range, right? Okay, so how can we, this is the one-dimensional range searching, which is a very important fundamental building block, okay, for some more complicated problem in the following chapters. So I think it will be a good idea to cover this chapter. The problem is like, okay, we have a bunch of points, okay. Of course, each point represents a number, okay. So this P, P1, P2, up to Pn, we have n numbers. Be the given set of points on a real line, because you can represent each number as a point on a real line, right? So a query asks for the point inside a certain range, okay, from x to x prime. Of course, x prime is greater or equal to x, okay. And at this moment, let's consider non-degenerate cases, okay. What do I mean by non-degenerate cases? I mean, well, we assume each point to have distinct coordinate value. Each point have different value. Okay. You may ask, like, how about if we have more points, happen to be in the same value? I mean, we can we'll deal with that later. Okay. But because this is one-dimensional, so if you have multiple points that happen to have the same value, then you are talking about the same point, basically, right? So you can sort of like have an extra field for each point to represent like if this how many multiplicity this point is. For most points, I think the multiplicity will be 1. But if you have multiple points, you can have, I mean, at the same location, you can have that point to have like a multiplicity to be more than 1, something like that. But let's not focus on degenerate cases. Let's just focus on like a non-degenerate cases. I mean, so we assume all the points have different value at this point. So the very easy approach, very efficient approach that we can deal with all these numbers will be the balanced binary search tree. You guys have been have seen that we have been using this balanced binary search tree in this class for many times, right? But in the past, we just say, oh, it's binary search tree. I mean, but we didn't really take a closer look on that, okay? Because we assume, I mean, well, you learned that from your data structure class. But now, okay, let's take a little bit closer look at this balanced binary search tree. Okay, so you can see that, okay, we are not talking about any balanced binary search tree, okay, because we are going to use this one, okay, for the one-dimensional range searching. Okay, so this balanced binary search tree is a little bit special in the sense that, okay, we have these two requirements. Okay, first, okay, the internal node will store the largest value in the left subtree. Okay? So second, all the point values, okay, will be stored at the leaf node. Okay, so here, okay, in this example in particular, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have, 13, 14. We have 14 points because we have 14 leaf nodes. Okay, the leaf nodes do not have to be at the same level. Okay, for example, you can see 49, 89, they are at different level. Okay, and then you can see each internal node represents the largest value on the left subtree. For example, it's 10. 10, okay, the left subtree, the largest value is 10. So we will put 10 here. This 49, because the left subtree, okay, the largest value is 49. So we put 49 here. These two things can be enforced when you construct this balanced binary search tree. I mean, very easily. Okay, so I will leave that in detail for you guys. Okay, and also, by the way, I just want you to be aware. Okay, even though we represent these things as a tree, okay, in the real data structure, okay, we certainly can put these numbers into an array, right? You know how to use an array to represent binary, binary search tree, right? This is, I know some students here may just have taken the master entrance exam at some schools, so this could be a good question in the exam. But really, this is one of the simple question for you, how do you represent the binary search tree by an array? Okay, you can think about that. Okay, basically, you can what is the relationship between the node and its left child and right child. For example, if a node index is I, its left child will be 2i, and its right child will be 2i plus 1. I mean index. Okay, their index. I mean, so it's very easy to represent this binary search tree in an array. Okay, so now, okay, given this 14 numbers, right? We have these 14 numbers. This binary search tree. Okay. Oh, by the way, the construction of this binary search tree, okay, balanced binary search tree, okay, is basically unlocked because there are two ways that we can talk about how to construct it. One way is you insert each number into the binary search tree. Okay, that's perhaps the first thing that came to your mind. Okay, how to construct this balanced binary search tree. The other way around is that, okay, you first store these numbers. You sort these numbers. Okay, from lowest to highest, of course, and then you put them into the array. Okay, you put these numbers into array in the way that I was just mentioned. Okay, and you will find that basically it's just kind of like just putting all those numbers in a linear order. So sorting, of course, takes a lot, and then putting those numbers into array takes linear time. So pretty much it's still a lot, but this is the second way to do it, because this is important because we are going to talk about, we're going to use this way later in this today. Okay. So now we have this 14 numbers. Okay, the construction time is unlocked. Okay, and then assuming we want to do a query in between the range, okay, say x prime will be from maybe 15 to 75. Okay, from 15 to 75. So how do we, it means like all the numbers between 15 to 75, so including 19, 23, 30, blah, 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 blah. This number up to 70 should be reported, right? Because they fall into this range, right? They fall into this range. But how do we efficiently do that? for 1D range search. Because we represent this binary search tree visually, so you can obviously see that, okay, once you are able to find the leftmost point to report and rightmost point to report, okay, leftmost point to report, say that point is mu, rightmost point to report, say that point is mu prime. Okay? Then what you need to do is just to report not only mu and the mu prime, but also all the points, in between these 2 points, right? Right? Okay. So what you want to find, okay, is the smallest point in this range and the largest point in this range, because mu is smallest point in between 15 to 75. Okay. Oh, I'm sorry. Okay, I let me correct myself, because we also need to report 80. So maybe 85. Okay, and the mu, 80 is the largest point within this range. Okay, and all the other points are in between. Okay, and so our problem become like finding these 2 endpoints. Okay, so how do we find these 2 endpoints? So we are given this binary search tree as well as the range. Okay. You will find that, okay, you will find that sometimes you may, because the binary search tree may have many layers. But for example, when you are here, you don't want to search the endpoint on both directions. Okay, there's a particular point that you will start searching the branch the search for the 2 endpoints. Okay, in this example, it's going to be this one. In the previous, in the example in this slide, it will be this one, because obviously the endpoint one endpoint will be on the left subtree, the other endpoint will be on the right subtree of this point of the root, right? So first thing first is that you need to find the point that you start splitting to search for 2 endpoints. We call that point split point, split node. Okay. So basically, okay, the split node, okay, in the remember, like we store for each internal node, we store the value we store for the node is the largest value on the left subtree, right? Okay, so as long as that value you stored is either smaller than the smallest, smaller than the lower bound, or larger than the upper bound. Let me draw it. So if the value I saw here, I mean the value I saw here will be the largest value in this subtree, right? Will be the largest value in this subtree, right? So if the range that I'm searching for, okay, say, let me give you a very concrete one, okay? Say this value is 50, okay? This value is 50. And if your search range is 60 to 100, this is your x, this is your x prime. Should you use this one as a split node? Is it possible? Is it possible? The lower, the mu will be inside this left subtree? It's impossible, right? Because the largest value in this left subtree is 50. And this 50 is already smaller than 60, right? Right? So we should, so this, I mean, since there's no, it's impossible to contain any node in this left subtree. So this is not split node. Okay? And similarly, say if our search range is maybe from 10 to 40, then we know that 50 is not going to be a split node either. Why? Because it's impossible for any node in this range to fall on the right subtree either, right? Right? So when will be, I mean, we will start to consider, okay, this node is a split node. It is when this node, okay, starting from root, if it is not in, if it is either smaller than the lower bound or larger than the upper bound, then we just keep going down. Okay, when we go down, of course we need to decide like which way to go. Okay, for example, okay, if it's larger than the upper bound like this, then we need to go down this direction to the right subtree, right? If I'm sorry, left subtree. We should go to left subtree. We should go to left subtree. For case like this, if it's like this case, okay, if the stored value is smaller than the lower bound of the search range, then we go to the right subtree, right? Okay, so we keep going down from the root, until when? Until we find the value, the value that stored in this one happen to be inside. It will be the first one that falls inside this range. Okay, starting from root, okay, you will find the first one that falls inside this range. That's the split node that we are talking about. Okay, that's the split node we are talking about. So basically, the algorithm is very simple. You can see that, okay, here we are searching for split node, right? We have a subroutine to search for the split node. The idea is very simple. Okay, we have a tree and two values, x and x prime. Okay, x is the lower bound, x prime is the upper bound for the search range. Okay, and we want to output the node v where the path to x and x prime split. Okay, or the leaf where both paths end. Okay, well, I mean, if you try to consider this as one path, this as a second path. Okay, these two paths end at the split node. Okay, that's how we can describe this in a different way. Okay, so you can start from root, and when well, this node is not a leaf node. Okay, if this node is a leaf node, then we are pretty much have to report it. Okay, that's the only node, right? If it's a leaf node. Okay, so as long as it's not leaf node, and you know, it's either smaller, well, it's larger than the upper bound, or x is smaller than the you know, lower bound. Okay, if any of the case happen, we keep going down. But how do we keep going down? If x, if the stored value is larger than the upper bound, we go to the left subtree. Otherwise, we go to the right subtree. So that's exactly what I was talking about. Okay, so this you can see obviously this quadratic n, I mean, will terminate under two conditions. The first condition is, well, V is a leaf node. Okay, then we'll return that leaf node. Okay, very simple. The second case is that, you know, xv is in between x and x prime. Right? And then that's the first node. I mean, we will return actually the first node from the root. I mean, that we have found that this node is, you know, its value is in between x and x prime. Then we'll return that node. That node is a split node. Okay? So after we found the split node, what do we do? Okay. Basically, okay, if V3 is a leaf node, okay, that's a special case. That's a special case. If that's a split node, then if split node is a leaf node, then we just make sure this split node, the value needs to be reported or not. Okay, it is still possible that this split node, I mean, even though it is split node, but because it's a leaf node, we report it. So we need to check if the value, if the value of this split node, I mean, fall into the range or not, the search range or not. If not, we shouldn't report it. Otherwise, you know, we'll report it. Okay? If it's in the range, we'll report it. Okay? So this is to deal with the case when V3 is a leaf node. Otherwise, I mean, it means that V3 is not a leaf, right? So basically, okay, we will follow the path X and report the points in subtree right of the path. What do I mean? It's like this. Say, here, we are looking for 15, remember? So, we know we split at this point, right? Okay, so we will go, I mean, for the x, okay, for the lower bound, we'll search for the lower bound. So we'll go this direction, right? Okay, from this split node, we'll search for x, 15, to be exact. So we go to, well, because it's smaller than 49, so we go to this node, left node. Okay, and then here it's very important. From here, because 15 is smaller than 23, right? We go 10, right? When we go to the left subtree, okay, all the points in the right subtree, all these 3 points, must fall in this range, right? Right? So what we do is we just report it. And we will just report it. Okay, same thing. Okay, well, if we go, well, 15 is bigger than 10, so we go to 19. Okay, we go to the right track. Okay, when we go to the right track, of course, we don't report left track. Okay, we don't report left subtree. Okay, but 19. Okay, same situation occur. Okay, 15 is smaller than 19, right? So we go to 19. Okay, we go 19. When we go to 19, we report the right subtree from the 19, which is 33. This 23 doesn't need to be checked. It must fall into the range. Right? And then the only thing we need to check is when we reach this node, we need to check if this node should be reported or not. And we do need to report this node because 19 is bigger than 15, right? Okay. So the basic idea will be like this. I mean, on the other side, the similar concept occurs. Okay, it's just like when you keep going to the right. Okay, when you go to the right, the left subtree, all the leaf node in the left subtree should be reported. Okay, so since you can see, okay, we go this way. Okay, 89 because say we are I'm sorry, from 49. Okay, we go to 80. Okay, say we are looking for 85, right? So 85. Well, yeah, I mean, it should be 75. I'm sorry. Okay, I made a mistake. Okay, 75. 75 is less than 80, right? So we go to left subtree. Okay, here you go to left subtree. Okay, you don't report anything here. Okay, and 75 is bigger than 62. So you go to right subtree. When you go to right subtree, you report all the points here. And 75 is bigger than 70, right? You go to right subtree and you report all the points here. 70, okay? But now, okay, you reach the leaf node. 75 is less than 80, okay? It's less than 80. So you don't report 80. But you do need to check this leaf node, right? Okay. The gray node, okay, here means the node you need to do the comparison with. Okay, you need to do comparison. The dark node means the node you don't have to do any comparison. You can report that directly. And the white node means well you can just skip that. You have no way to touch that. Okay, so let's look at this algorithm. You can see, okay, as long as V3 is not a leaf, okay, you first go to the left subtree, okay, left subtree. And then while V is not a leaf node, okay, you do it if this if the one you store is bigger or is bigger or equal to x, is bigger or equal to the lower bound. Okay, if that's the case, you need to go to the let me see. We are that's a tree. So if yeah, in this case we need to go to the left, right? We need to go to the left. So when we go to the left, okay, I mean you report all the nodes in the right subtree first. So you do a report subtree, RCD, okay, the right child of D, okay, and then you go to the left child, okay. Otherwise, you just go to the right child, okay, and do nothing. Because this is a while loop, so you keep doing that until you reach the leaf node, okay, until you reach the leaf node, okay. So basically, that's about it. And this is one half of the code. Okay, the other half of the code will be similar to this one. It's just check if the point store and the leaf node, blah blah blah. This this description basically just means we have the other part of the code. Okay, so that's about it. So how much time does this algorithm take? Because think about this, okay? We are pretty much going to do to follow the path to two ends, right? So the path to one end takes log n amount of time, right? So you have two log n's, right? And then you also need to report a point in the middle, right? The point that you report in the middle, well, you guys know like that those are basically just tree traversal, right? The tree traversal basically takes the linear time to the number of points that you report. Okay, so so if you have you know n points, okay, it uses big O n storage. As I said, I mean you can use like array to store this binary search tree, and it has n log n construction time. I already explained. I mean, to how to construct this binary search tree. Okay, and then okay, such that the points in the query range can be reported in time big O k plus log n. Okay, the log n, you need log n because you are going to find two ends. So those takes like this many log n amount of comparisons. Okay, and the k represents the number of reported points. K basically take care of the points that you report in between the two ends. Okay, so this is a one-dimensional situation. Very simple, right? Very simple. Okay, so now, okay, we need to, okay, we are done with one-dimensional case. Let's up the game. Let's up the game. Let's start consider two-dimensional. Okay, let's start consider two-dimensional. Okay. Well, it's about time. Let's take 10 minutes break. When we come back, we are going to discuss the two-dimensional range search. Okay?